Hello, my name is David De Roure. I work in digital humanities, and for many years my personal research has been in the field of digital or computational musicology and music information retrieval. So I'm based at the University of Oxford and the Alan Turing Institute, which is the UK's National Institute for Data Science and AI. Today I'm going to tell you about my digital musicology journey because it's also been a journey in computational archival science. I hope you'll find this interesting and perhaps get some useful glimpses of ideas and practices. Before I go any further, I want to thank my many colleagues who've shared this journey with me over the last 2 decades. So while this talk is a personal view, all the work I'm presenting has been done in collaboration with an amazing group of people to whom I'm immensely grateful. In fact, I think it will become apparent that community is one of the themes of this talk. Thank you to all these people and more. I'm going to start by talking about digital scholarship and show you a couple of big picture lenses which establish the perspective for the rest of the talk. And these are social machines and citizen science. Then, with even more alliteration, we take a look at music in particular with a quick tour of several projects, and we pause amidst this to think about automation and artificial intelligence, which is the theme of our creative journey to the end of the talk, and I'll finish with some reflections. My first perspective is knowledge infrastructure. Paul Edwards wrote, "Knowledge infrastructures are ecologies or complex adaptive systems. They consist of numerous systems, each with its unique origins and goals, which are made to interoperate by means of standards, socket layers, social practices, norms, and individual behaviours that smooth out the connections between them." For me, everything around us is our knowledge infrastructure, so this workshop, for example. And I like this picture from the cover of Paul's report because it reminds us that we are trying to step outside and look at the knowledge infrastructure as a complex, dynamic, evolving artifact. And this enables us to consider aspects of computational archival science and the relationship between the infrastructure and the scholarship. It's sometimes hard to get this view when we sit inside the infrastructure as cogs in the machine. My second big picture describes the evolution of our knowledge infrastructure over time. So on the vertical axis here, we have the increasing computational capability, more cores, more memory, it's Moore's law. This is a really well understood and well forecast axis. On the horizontal scale, we have more people, the increasing engagement of scholars and citizens alike in the digital online world. And you can have some fun putting things on this picture. So for example, Science 2.0 is over on the right, while cyber infrastructure, e-infrastructure is up towards the top. The really interesting space for our discussion today is that top right quadrant, where people and compute are coming together at scale. And that's the space of digital scholarship today. And we can ask, where is it going tomorrow? So we're seeing increasing automation, for example, to deal with scale. And this for me is very much the space of computational archival science. As time goes on, we might run out of people, but the computers seem to be getting more powerful and more informed by more data as they learn from us. So we have an important machine learning dimension too. This is a really complex socio-technical space, and it goes by many names, from social computing to human computation. We don't have so much theory to describe it and to design in it, but one that I've used a lot is this idea of social machines. So back in 1999, before social media as we know it today, Tim Berners-Lee wrote, "Real life is and must be full of all kinds of social constraint, the very processes from which society arises. Computers can help if we use them to create abstract social machines on the web, processes in which the people do the creative work and the machine does the administration." So that's a really important principle of empowerment. Computers assisting humans, not replacing them. But the rest of that quote is often missed out, but it's crucial. The stage is set for an evolutionary growth of new social engines, the ability to create new forms of social process would be given to the world at large and development would be rapid. And that is exactly what happened since 1999. Look at the new social processes that emerged in social media like Twitter and the speed that this occurred. So let's look at a social machine in our knowledge infrastructure, a scholarly social machine, citizen science. So Zooniverse, for example, which comes from the next building to me in Oxford, is a major citizen science platform which reaches across all disciplines. Now, it started off with one project, Galaxy Zoo, and then it became a platform with new projects being released all the time, and then evolved again so that anyone can build a project. So it's a platform for creating social machines, and it certainly demonstrates scale, with 500 million classifications now by over 2 million volunteers. Why is Zooniverse a social machine for citizen science and not just crowdsourcing? And this was explained to me many years ago on a blackboard in the physics building. The crowd of humans could each make independent classifications of galaxy images, and this would provide the scientists with statistical outcomes that they want. But what actually happens in Zooniverse is that the volunteers have their own discussions, and through this they have made their own discoveries. So this human-to-human interaction is, for me, what makes it a social machine. The humans are engaged in the science and they can create new social processes. So let's have a look at that original project, Galaxy Zoo, today. Reading from the webpage. In an effort to speed up classifications to cope with the large number of galaxies we expect to receive from new surveys, we've been working on ways to combine your classifications with those of machines. Okay. Now, if you choose the enhanced workflow, you'll be much more likely to see the top 100 galaxies that the galaxy classifying robot thinks it needs help with in order to improve. On the other hand, we keep humans in the loop, so all galaxies will be seen by at least a few volunteers to make sure we aren't missing anything. And if you don't want to opt in for this AI thing, if you'd rather just see random available galaxies, you can choose the classic workflow. So we've now set the scene, our big picture of digital scholarship, and now I'm going to turn to music. So the first thing to say is that music comes in many forms, many representations, from musical scores or player pianos to wire, wax, digital audio recordings. And traditionally, musicologists might have studied musical scores in the library or archive, but today we can extract features computationally and use these as the basis for analysis, and this is the field of digital musicology. Musical compositions can be reproduced, perhaps as sheet music or recordings, and they can be performed, which may lead to further recordings and representations. One thing you might ask yourself, illustrating the complexity of this field, is what does it mean for two things to be the same piece of music? Our fundamental challenge is to go from that music signal in whatever mode through to some kind of understanding. And in fact, the specific area I'm interested in is determining the structure of music, as in this piece of popular music. In fact, this picture nicely captures the task of making sense of the signals in our archives, musical or otherwise. And that's why I think that the techniques of digital musicology may be more broadly applicable. And how is this done? Well, the answer is by humans and by machines working together, or if you like, a social machine. So the Murex Music Information Retrieval Evaluation Exchange has been running for about 15 years. It brings together a vibrant community in an annual challenge. So each year, the community decides which musical features to focus on, for example, key detection, mood classification, genre classification, fingerprinting. and then they innovate and evaluate their algorithms to produce results which improve year on year, and they're published in summary tables. Being careful to note, though, that this is not a competition, it's an evaluation exchange. There are many interesting things here. Although there are obviously some shared corpuses of music in use by the community, the test data isn't open, and the testing is done over a corpus in one central location. So this means that people submit code which is executed over content that they don't have direct access to, and this is the non-consumptive research model. It overcomes a constraint of working with copyright content, and which is relevant to archival work in general, but we could also draw a parallel here with working with archives of secure or sensitive data in other fields. Now, I said I'm interested in musical structure. What do we mean by musical structure? What I'm referring to is the repetition of parts of the music in a piece, like the earlier example with verses and choruses. This repetition can occur at a far more detailed level, a sequence of notes or chords which recurs. These arc diagrams illustrate this repetition. In fact, these particular diagrams show analyses of the human and AI parts of a piece of music co-created by human and AI as part of an ongoing analysis in my current research, but more of that later. Arc diagrams are used as visualizations in other areas, for example with gene sequences. And so too, structural analysis of large amounts of music information, or SALAMI. I once claimed this was the best project acronym ever, and my colleague Daniel Bangert at least agreed that it's not the first. The left-hand side of this picture describes how we collected the, quotes, ground truth, annotations by human experts of 1,400 musical recordings. And analysis on this scale was unprecedented. How did we do it? With a social machine. We crowdsourced it, or in fact we grad-sourced it. We then used this ground truth in conjunction with the Merrick's structural analysis algorithms to automate the analysis and compare the results. And just to note, therefore, that Murex is a social machine too. We asked our annotators to identify both large-scale and small-scale structure, and we set out to avoid conflation of music similarity, function, and instrumentation. So to give an example, our earlier piece had a chorus and an outro. They have different functions and different labels, but what if they were the same bit of music? So we designed the annotation scheme carefully based on several previous studies. The tool we used for annotating the pieces is called Sonic Visualizer. So the student first listened through the song and marked the structural boundaries as they first perceived them. Then in a second listening, they adjusted boundaries and added those lowercase labels. And in the final passes, they added the uppercase, the function, the lead instrument labels. It was a time-consuming process. Here you can see an example of some of the timestamps annotation. And the results of these analyses were published as a dataset on GitHub and a paper in the Izmir conference. Finally, we were able to compare the humans with the algorithms, and the interactive tool enabled the music to be played back and navigated by structure. And we could compare apparently similar fragments by playing them back simultaneously. And I felt that this tool alone was an interesting outcome of our information retrieval exercise, because it allows easy navigation of the archival content based on annotation, something that Computational Archival Science can help with. As Murex has progressed, some scholars have noticed that there seem to be some limitations that prevent results going beyond a certain point. This has been described as a glass ceiling, and it's an interesting kind of meta result in our Murex social machine as we study the studies. So one contention is that we need the musicologist to bring in some music theory to move this to a higher level. After all, digital musicology doesn't set out to replace musicologists, but to enable and empower them. So Transforming Musicology was a project in the Arts and Humanities Research Council Digital Transformations Programme. Essentially, the strapline was, digital has transformed music, now it's time to transform musicology. And credit to project lead Tim Crawford at Goldsmiths for this vision. Again, I'm just going to highlight a couple of aspects which I think inform computational archival science. I notice here the framework enabling data, methods and results to be shared permanently as linked data and enhanced semantic web workflow descriptions. The team in Oxford has successfully used linked data through multiple projects, including Salami, Transforming Musicology, and most recently the International Linked Art Project. And with credit to Terry Numiko Fuller, here's one of the semantic web ontologies from Transforming Musicology in full colour. Today we see the opportunity much more broadly to link music catalogues and digitised holdings, fully embracing that multimodal nature of music that we've seen in these projects, an area being developed by my colleague Kevin Page. Linked data is how to reach across and join up our archives and reach across our knowledge infrastructures, and it's designed for processing by machine, so I think that definitely makes it part of computational archival science. Secondly, data collection again. Once again, we thought hard about the user experience. And here is an annotation interface that we built so that the musicologist, Carolyn Rindfleisch, could perform live annotation throughout a performance of Wagner's Ring cycle. And for those of you who know the Ring, you'll realise this was an epic endeavour of several days. And this is a reminder that in the process of all our projects, like the Salami annotations, we're creating the archive for tomorrow's research and sharing the methods too. It's surprising how often digital humanities research projects that are using archives don't actually think about the archive they are creating for the future. And we should be making those archives, which can be quite big, ready for computational archival science. So Murex, Salami and Transforming Musicology all made use of workflows. And I just wanted to say something about that, about automation. And then we'll come back to music in a minute. So back in 2007, when Amazon sold books and MySpace was the latest thing, we launched a website called My Experiment, which is a social website for sharing workflows. And the sort of workflows shared on My Experiment are computational. They're executed by computer in silico, if you like. They are a means to automation in our research, much needed as our data volume scaled up. And for example, we have many in bioinformatics, but the workflows are across all disciplines. And computational workflows are also really useful for that non-consumptive research we mentioned earlier, as in running the code in Murex. So sharing workflows is a way of sharing methods and a way of recording and reproducing our research for our communities and for our future selves. There's been a lot of emphasis on data sharing, and of course this is a really good thing, but I would argue that sharing the processes is important too, at least as important, well, maybe even more important. At the Joint Conference on Digital Libraries in 2013, I used this slide to talk about the future. It came from working with My Experiment and realising that workflows could be run automatically and that they could be repaired automatically, a sort of autonomic curation. So imagine dropping a new data set into a repository and a new set of papers are produced automatically because you triggered the workflows. In practice, a great many workflows are essentially doing housekeeping. They're actually helping just to curate the archive, which of course is hugely important too. And I think that definitely makes them part of computational archival science. The other thing we did in My Experiment was introduce the notion of research objects. These were workflows bundled with their related data, inputs, outputs, tests, papers, slides. They're uniquely identified and they're shareable. So we introduced research objects to the world in a paper back then controversially entitled "Why Linked Data is Not Enough for Scientists." And so we fast forward to fusing audio and semantic technologies, our next music project. It's an acronym, but it's not salami. FAST was a big project led by Mark Sandler at Queen Mary, University of London, and it looked at the entire music production pipeline, from composition to performance to recording to production to distribution to consumption to reuse and archiving. And not necessarily in that order, as the traditional production chain has given way to the affordances of the digital. Till now, this has largely been done with audio files like it used to be done with magnetic tapes. Our contention was that by capturing metadata at source, by capturing the workflows, the provenance, and by building all this into digital music objects, we would have much richer and more reusable content. And incidentally, I would say exactly the same thing for science, but that's a whole other story. So I'd like to share my 3 favourite outcomes of FAST, and the first of these is the SOFA, which stands for the Sofa Ontological Fragment Assembler. So while the research object world has become a bit preoccupied with semantically described containers of stuff, our digital music objects are rich computational objects that wrap up multiple structured digital music content types with rich metadata into a kind of musical essence. So what we have is semantically described fragments which can be assembled automatically. We also found these FAST diagrams really useful. So they were invented by Steve Benford in Nottingham. And here the x-axis is the activity from production through to consumption and every stage in between. The y-axis is the people, the involvement from professional to amateur to audience. So individual projects within our program would feature as a region, as on the left picture here. But also you can visualize activities and tools that move around the space, tracking the flow of those digital music objects. I offer these diagrams in the hope that they might be useful to you too. Can we use pictures like this in computational archival science? The other thing from FAST is our semantic signal generator, or fragments generator. It rhythmically generates synthetic data that we use to test our toolchain. The software is called Numbers into Notes. It was inspired by Ada Lovelace and Charles Babbage, and it's also been used in compositions. More from Ada Lovelace in a minute. And in the spirit of reproducibility, as well as generating data, our tool provides a provenance graph. Here it is in W3C prov notation, so that the process that generated the data is well described. So now we've discussed workflows and we've mentioned provenance. How do these two fit together? So they're both descriptions of processes. One is retrospective, one is prospective. A workflow is a plan. When you've enacted the plan, then you can have a provenance record showing what actually happened. So this diagram by my colleague Graham Klein is an exercise in fitting things along a retrospective prospective axis, but also interestingly a deterministic creative vertical axis. I wonder if computational archival science is, by its nature, a lot more about the prospective than archival science has been before. It's a thought for discussion. And now for a little music. We can't have a talk about music in the archives without a little music. I've chosen this piece by my colleague Alan Chamberlain because it draws together pretty much everything that we've been talking about. And I'll leave you to read the program notes and to think about process and provenance and also algorithms in the archive. Throughout this talk, we've seen the interplay between human and machine as we've welcomed in automation to help with the scale of our challenges. And in our work, we've brought the public into a conversation about the role of artificial intelligence in music composition. So, working with mathematician Marcos de Soto, composer Robert Laidlaw created some pieces of music which segued seamlessly back and forth between real bark and AI-generated fake bark. These were performed by human in front of audiences who then had to decide when the composer was human and when AI by holding up coloured cards. So this was performed at the Barbican Centre in London, at the Royal Northern College of Music, and at the 2019 Royal Institution Christmas Lectures. You can find that last one online in Lecture 3, How Can We All Win?, just before the closing credits. But our goal isn't human versus machine, like some blockbusting movie. Our goal is to explore how AI can assist humans co-creatively, which is what this talk is about. Robert Laidlaw went on to compose Alter, the first contemporary classical composition that was created both with AI and about AI. For Alter, Rob used archival content. So we took the transcriptions of Lovelace correspondence in the Bodleian Libraries, box 170, and we used it to create a kind of Lovelace ghost, which Rob prompted to generate the text for the piece. But the English language models used popularly in AI today are typically based on the web, and what we needed was the 19th century language model. So we trained our AI on some of the content of the electronic Enlightenment corpus, also at the Bodleian. In a way, we needed the literature and language that Lovelace would have consumed. And this suggests an interesting future line of work where we build ghosts of historical figures based on their book collections, their personal libraries. It's also raised for us the vexed question of whether to train our Lovelace on the works of Byron, since her mother evidently denied her access to her father's work. Anyway, what we have here is a computational and creative response to archival content. And now let's hear from the composer himself, Robert Laidlaw, about the AI in Alter. And then I have some questions.
So the narrative of the piece, programmatically, is that we're going to hear, hopefully, the birth of a kind of artificial mind from very first creation to not being sure where it is, what's going on, discovering that this program can go back and alter itself, and it does this a couple of times, and each time throughout the piece it becomes more and more developed and more self-aware. As we were developing the piece, we were developing new AIs as it goes along, so the text you're hearing at the beginning is literally less sophisticated in its algorithm than it is at the end. We thought that was quite exciting to take moments from different parts of the machine learning process.
So thank you to Robert. Now, I have some questions for you about AI and the archive. If we train our AI model on copyright content, can we make that model available? So this arose in Alter. We were explicitly given permission to do the training, but what can we do with the trained data set? What is it that we want to archive? Is it the training data? Is it the models? Is it the content generated by the AI? This is all definitely computational archival content. And thirdly, do we actually need to archive all this synthetic content if we can simply regenerate it? A teasing final question might be, can we throw away archival content if we can rebuild content on demand that can't be distinguished from the original? But I do see that's a bit controversial. So that's it. It's time to sum up and leave you with some final thoughts for the future. I'm hugely grateful to my colleagues in the Computational Archival Science community, several of whom can be seen in this picture, which looks a little bit too much like a 1970s prog rock gatefold. I hope I've illustrated a few practices from my digital musicology world, which might inform our discussions. So feature extraction, navigation, linkage, automation, creative responses. And we've seen the computational use of the archive by researchers, but also the use of computational tools to curate the archive and to support search and discovery, or even to do research. I hope you find that the lens of social machines is useful too. I leave you with a future research topic, another meta-analysis. So scholarly primitives were described by John Unsworth to refer to some basic functions common to scholarly activity across disciplines over time, independent of theoretical orientation. And they are functions that form the basis for higher level scholarly projects, arguments, statements, interpretations. And rather than a definitive set of primitives, they provide a method for reflection. So, for example, they've been revisited in the context of crowdsourcing by our colleagues at King's and in my work on scholarly social machines with Pip Wilcox at the National Archives. And some of our primitives are shown here. My question to you is, what are the scholarly primitives in the context of computational archival science? And to close, a famous quote from Marshall McLuhan: "We become what we behold, we shape our tools, and then our tools shape us." And when I talk about knowledge infrastructure, I sometimes say we shape our research tools, and then our tools shape our research. Because although we like to think that the infrastructure responds to our research questions, we also know that it can influence those questions. And for archives in particular, perhaps we might say we shape our archives and then our archives shape us, which I think is a powerful statement and something gaining increasing recognition. So, what do we behold in computational archival science? Because that is what we will become. Thank you.